So really quickly, there's sort of a slide each on the Passive House standards on net zero energy, which you'll see pretty quickly. I consider all the same thing. Then we'll sort of discuss cold climate applications, as in, you know, we've been doing this stuff here for about 10 years. What have we learned? Hopefully something. And then we'll kind of review some project examples, or sort of our favorite project examples. And at the end, there's sort of a little bit more in-depth review of the most recently completed 50-unit passive house for BC Housing in Fort St. John, BC. Very quickly, you know, what is passive house? This is the most, I think, easily recognized definition of passive house. This is the PHI standard, the German standard. 3 targets. There's an annual heating and cooling demand target, 15 kilowatt hours a meter squared. There's an air tightness target, and then there's primary energy. Really, in a nutshell, what this standard is trying to get you to do is conserve energy. So they set out and said, well, if we, you know, want to stop climate change, we want to create energy efficient buildings that use our fair share of energy for everybody. This is the most cost effective way to do it. The Germans said this. That primary energy target is defined based on carbon emission targets, and if everybody used that level of energy in buildings, we would meet our sort of carbon mitigation targets moving forward. So that's the very fundamentals of it. That standard came to North America late 2000s, and in the next decade, the Americans sort of spun off a different version. I guess quickly, these targets are the same everywhere, whether you're in Alaska or you're in Miami, which means it's of varying degrees of difficulty to meet the standard. Basically, the more extreme your climate is, the harder it is. The Americans said, well, that's silly. Why don't we do our fair share everywhere? And they decided to create energy targets that are specific to each climate, which was a cool idea, but it added a lot of work. And this standard has been around, like I said, about 10 years. The 2018 version is out now, and frankly, it's getting really complex. Like, these are my sort of frank notes, but you're almost getting to the point where each project, not even each city, but each project has its own performance targets that it needs to meet, which you can imagine is therefore way harder to facilitate, design for, get costed. You know, if someone says, hey, I might want to build a passive house, what's the premium for this? You know, it's one thing for PHI, it's the standard that's always been around, but it's another thing for PHIUS now. It's like, well, what's the target for that project? I don't know. How big is it? What's your occupant density? What, you know, where's it going to be? And you have to start doing this stuff. So these standards are out there, just for reference. And then lastly, net zero energy. This is the simplest, probably most poorly defined sort of standard or target out there, but it's easy to understand. Basically, the building needs to produce as much energy as it uses on site in a typical year. There are subtle differences in definitions. Different institutions have different definitions. We're hopefully going to see, you know, over the next 5-10 years, that definition become, you know, more solidified as one. But anyways, it's out there. So what have we learned in 10 years of doing this? Basically, it's really hard. The international standard, I would almost say, is, like, it's not impossible, but it's extremely difficult. As an example, a cube, take a building that's 50 feet footprint square, 25 feet tall. If you put R100 insulation effective on all surfaces, had no windows, and you had the air tightness target met, you would not meet passive house. So that's like, what does it mean? Well, to actually meet the standard here, then you have to design windows that have a net benefit to the building. You have to actually heat the building with your windows, which is really counterintuitive traditionally. So, you know, there are tricks to doing that. But it means you're turning to solar gains to heat the building. Now you have to get really intelligent about letting the sun in when it's heating the building in a helpful way, but then not letting it in when it's overheating. Overheating becomes quickly this, in our climates around here, overheating becomes a concern. If you have conserved enough to drive down the heating demand to within those targets, you have a cooling problem, unless you're being very rigorous about that. So it's kind of what I'm saying. The lessons here, you know, actually certified PHI or PHIUS buildings, we're sort of seeing envelope overkill to hit the targets, sometimes doing silly things, and then we have to deal with this overheating thing. Short story, what have we seen come out of this as the happy medium, the really good building approach that's cost effective, gets pretty much all the benefits, and is, you know, sort of picking up steam? That's net zero energy. So that's why this is all here. But not net zero energy where you have a standard code building and you just throw PV on the roof. It's using the passive house methodologies to conserve to the point that it makes sense, and then turning that over to production with PV. Quickly, I'm going to rip through, I think it's 5 project examples here within this context. So the first 3 are certified passive house projects. This first one was the first one. This is the Cottonwood Passive House in Fort Saskatchewan. This was the first certified passive house in Alberta. This was back in like 2012. It was really groundbreaking. This was, you know, right around the first passive house in Western Canada, and certainly the first one in a cold climate. There were some ones in Surrey and on the island, but it's much easier to do there. And here's where we get technical. So this is a graph. Annual heating and cooling demand. The red is heating demand, and the blue is cooling. If you can't see, that's January, and then we're rolling through monthly. So basically, dead of winter, you can see lots of heating profile, you know, tapers off, and then we start to see cooling in the summer, and then we're back in the fall, and then, you know, we're back into heating. So this profile is not that different from, you know, a code-built equivalent house. You know, from a cooling perspective, that curve is about the same. The heating demand for the code-built building would be 10 times higher. So what we've done, and this is the whole deal with passive house, is we've used building envelope performance to drastically conserve the amount of heating demand required to the tune of like 90%. And then, like I said, now what's left is this cooling bit, which is now almost an equivalently pressing problem to the heating needs that actually need to be met. Theoretically, you could design a passive house that did not have this bump in the middle, but that would require like absolutely militant attention and sacrifice on the glazing design. So like I said, you'd only have the windows that offer net heating. You would not have any other windows. Whereas this project, I think, views a golf course, and of course, you know, these guys are building a nice house, retirement house. They want to live in it and enjoy it, so naturally they put windows where they wanted windows, and so there's a balance there, right? And so what I'm saying there is that perfectly optimized project never exists, really. And so that's where the cooling starts to lurk, and you start to have to deal with that. So anyways, that was the first around here. This is the Valleyview Townhall in Valleyview, Alberta, certified passive house. So when you shift this sort of application of building science methodology into a commercial building, now you've got way higher internal gains. In a house, you've got people, they're not really doing much in there. They might have a TV, they might have, you know, the cooking and stuff like that, but there's not a ton of equipment, and there's not a ton of density, right? You might have, you know, 4 people in 2,000 square feet or something like that. Whereas now in an office, you've got way more people, you've got way more equipment, you've got lights that are on all day, and so the internal gains are suddenly way higher. And so what does that do? Well, it bumps up your cooling profile. You can see that the peak cooling load in demand terms is higher than heating. So this is in Valleyview. That's cold. That's a little bit colder than Edmonton, right? And this is after we've paid utmost attention to intelligent lighting design. We're not over lighting. We're using the most efficient fixtures possible, using day lighting. But this is basically the optimal result that we end at. And if you think about it, then what would be the benefit of adding more insulation to this building, to this profile? You would see a reduction in heating, but you'd see an increase in cooling. And so that's where, like, there's always a diminishing return to extra insulation. Like, you can do the math on that. But in passive house, near the extremes, once you've already like this project had our 60, 70 walls, like really, really thick, super insulated assemblies. And if you think about what happens from R50 wall to R60 wall, as an example, with this kind of profile, it's going to shift the heating down and boost up the cooling. Well, are you winning? Maybe, but the return is smaller and smaller every time. The only way you're winning is really because the efficiency of cooling systems is higher than heating, especially with an air source heat pump type heating system, which is what this project has. Anyways, these are lessons. So, this is, as an example, a municipality that said, we want to build a certified passive house town hall. So they did it. But and here's the lesson learned, if they said, build us the most cost-effective, high-performance building, the recipe would be a little bit different based on our learnings. And it has to do with this cooling stuff. Here is the 50-unit passive house in Fort St. John. Same deal. This is BC Housing saying, build us a certified PHI passive house apartment project, 50 units. And wow, look at that. Look at that cooling. This is Fort St. John. That's significantly colder than Edmonton. Our Edmonton design temperature in the city is -28, and it's -38 in Fort St. John. Quite a bit colder, and still, this is actually cooling dominant. And then you might say, well, that's kind of silly, and you might be right. The things, and like I said at the end, we're going to go a little bit more in detail into this project, but this one fought the site. They ended up having to do a north-south double-loaded corridor, which meant that that's the west facade. So like the elongated facades of the building are west-facing and east-facing, which is completely not passive solar design, right? But this is the reality of this, is someone says building this project on this piece of land, well, you have to work with what you have, right? Which means your passive solar gains, you're fighting it all away. Like if you accept those gains in the winter, you're definitely getting them in the summer. You can't control solar gain. Virtually impossible to control solar gain on the west and east facades without like rolling shutters and stuff, which are really, really expensive. So now let's shift gears a little bit. Here's our most recent projects, as in under construction. And here's the net zero energy flavor. So these are, this Morinville project, it's an Alberta social housing project. Our team responded in a design build fashion successfully, and we said to their RFP, we will build you net zero apartments for your standard budget. They didn't ask for net zero, and we responded and said we'll do it. And we're doing it to date. But so what that means is that nobody said thou shalt passive house. They said let's use all the tools available and build the most cost-effective, energy-efficient thing we can. And this is where we landed. Peter Amarongan's been heavily involved in this one as well, and leveraging his 4 decades of experience with this. But where we ended up is like 35% R value than passive house, and you can still see this curve. So we're still cooling dominant. So in this case then, take this curve and then add 35% more R value. That heating demand just is going to disappear almost, and it's all cooling, which is again kind of silly. And it stops making cost-effective sense. And so this is the latest one, the next sort of iteration in Fort St. John. That city is a real center of leadership with this stuff. So they're doing, and they set out to do a passive house RCMP detachment. But they've had enough experience with these projects, this is the third one in that area, that they said, well, we're not just totally stuck on passive house, let's do what makes sense. Let's do what we can sell our taxpayers on. We don't want to be seen as wasting money. And so same deal, we did a in-depth cost analysis, and we again landed on passive house inspired net zero energy. And here I actually have the numbers to compare the difference. Net zero is a 10-year faster payback, and it only uses 1.5% less energy annually than passive house. It's pretty compelling. And you can see, again, it's cooling dominant. This project it's in, that the continuation of internal gains being the dominant thing that we're grappling with, that's even greater with this project because it's a 24-hour occupied building. So now we've got all night, the lights are on all the time, and that's internal gains, and that's in the summer that's overheating, that's doing all this stuff. So even optimized, you can see we're looking at a cooling dominant building. This is the rough modeling that we've done to date. Basically, we're militantly trying to control internal gains, and solar gains is part of that. And so we've got an east-west elongated massing, only glazing on the south and north that's there for daylighting, and there's none on the west and the east. And so, as I said, that Fort St. John 50 unit passive house was kind of the opposite of that, and so we were fighting it. Here are some numbers for that project. So, and this is where it's technical, and I apologize if you're not a technical person, but net zero ready, which is our passive house optimized building stopping when we think it makes sense, but not putting PV on it. When you put PV on it, it becomes net zero energy. That's net zero ready, if you follow. Basically, compared to a base code design, that net zero ready building is a 21-year payback. For an owner-operator, that is a glorious win. You know, these guys, the city of Fort St. John is going to own and operate this building for 80 years probably, at least 50. And to have a 21-year payback, they're winning. Like, this makes economic sense. Forget climate change. This is the most cost-effective thing that they can do. This column, add PV. What does it do to the payback? Nothing, because the payback of PV is 21 years, or it's 18, 19 years. But what does it do to life cycle cost? It actually reduces it. So right here we have the net zero energy design. It has the lowest life cycle cost, 30-year and 50-year, and these are all simple numbers. There's no inflation or escalation or any of that. But it is the lowest cost building that this city can set out to build. And to me, that's extremely compelling because it's also zero carbon. Here are the passive house comparators. So this is the PHI building, with the same amount of PV, and then the PHIUS, the American Standard building with, and then the same amount of PV again. And you can see, what does it do to payback? It adds, 7 to 10 years. And the cost premium, so forget about the PV for a second. So compare PHI to net zero ready. That's about a $500,000 premium, these two numbers. It's doubling our values. Like, the net zero design is our 20, subgrade foundation works, about our 30 walls and our 50, 60 roof. The PHI design is literally double that. It's like our 50 walls, our 30 sub-slab, and our 120 roof. So $500,000 premium. The PV system to make this net zero is $375,000. So you can literally build a net zero building plus the PV on it for less money than the certified passive house. So as a huge proponent of passive house, I say you have to look at the numbers and do what's practical in each case. Basically, what are the HVAC, this is the heating, cooling, ventilation implications of building this type of building? Well, basically, the envelope guarantees thermal comfort. You don't need radiant heating systems. You don't need perimeter, radiators. There's no drafts. You can downsize the distribution of your mechanical and save some money. Our 90% HRVs ensure we can deliver fresh air without being tempered, which again saves a lot of energy and space and everything else. Ultimately, as you've seen, these buildings need cooling. They almost need cooling more than they need heating. Like, they would, they need heating, but. And so how do you do that? Well, an air conditioning system that can heat would be great. Well, that's a heat pump, right? So an air source heat pump, ground source heat pump, that's where we're at. Coupled with ERVs, this is the technology we're picking. Okay, I have 30 seconds, so I'm going to rip through this. Here's the 50 unit passive house completed. There's the team. This is the site that I talked about. And they were forced to basically put the building on this footprint, and that was the architect's decision, but it wasn't up to them. Basically, there was site servicing things that conflicted. So not ideal. Not ideal massing. Here's the certified passive house. Our values are 45, 55, 90, pretty extreme. This is the HVAC system we used. As I mentioned, it was essential Swagon ERV and a Daikin VRV system. It's air source with gas unit heater backup. So we enclose, basically these VRV systems will work at this time. This one would work till -20 and then it would cut out. And so we said, okay, well, we're going to use it till -20 and then we're going to put a tent around it and heat the tent, below -20. And that's what this is. So these things are sitting in on a pretty poorly insulated penthouse with duct louver setups that basically at -20 there's a changeover and they become a recirculation device, and then there's unit heaters in there that provide heat. On our newest projects, we're using Daikin's latest model. It's good to -30 and below. We're actually using it in that Morinville project with no backup. So that's air source heat pump on a 50-unit apartment building with no backup. And we're quite confident it's going to work. That's just some VRV stuff. That's how this is the super minimized ducting distribution in a suite. We basically just have to get some air into the suite. We don't have to get it to the windows. We don't have to worry about that thermal comfort. Here's the project completed. Thanks.